Okay, today we discuss about characteristics of pulse waveform. So the voltage level of the top of the pulse with respect to the ground is pulse amplitude, or it is also called as a magnitude of the pulse. The edge of the pulse at t equal to 0 say is called a leading edge or the rising edge or a positive going edge. The second edge at a time t equal to t1 is called the trailing edge. It is also called as a falling edge or the negative going edge. The time interval from the leading edge or a trailing edge of one pulse to the leading or a trailing edge of the next pulse is time period t. The reciprocal of the time period is the pulse repetition frequency. The time interval from the leading edge called pulse width is called the pulse width. This is the leading edge. This is a trailing edge. So here this is a leading edge. This is a trailing edge. And this is called pulse width from leading edge to falling edge. From one leading edge to another leading edge is a time period. 1 by time period is called pulse repetition frequency. This is the pulse characteristics. Suppose it starts from 0, but here it is sudden. This is ideal case. In practical cases, it is not sudden. It is somewhat exponential, remains constant, then decreases, falls to 0. From 0 to up to 10%, up to 50%, up to 90%, then up to 100%. So in this way, it is divided. The pulse starting from 0 to 10%, 0 to 10% is known as TD, is known as TD, delay time or time delay. From 10% to up to 90%. From 0 to 10 it is called TD, delay time. From 10% to up to 90% it is called a rise time. It is called a rise time. Then from 90% to 10% falling edge, it is called fall time. And from 100% to up to 90% it is called storage time. Fall time, storage time, delay time, and rise time. The period from 10% to 50%, 90%, 10% to 90% is called on time. From 100% to 90% it is called off time. 100% to 90% it is called off time at the falling edge. At the rising edge, the time between 10% to 90% is known as on time, and at the falling edge of the pulse between 100% to 90%, the time duration is called off time. So now duty cycle, the ratio of pulse width to the pulse period. Pulse width is simply one pulse. So this is a complete waveform. So this is called On period, this is called off period, from here to here, from here to here. This is on period, this is off period. Duty cycle is a ratio of pulse width, width of this pulse, any one of the pulse, either this or this, divided by total period for on off into 100% is called a duty cycle. Rise time, time it takes to rise from 10% to 90% of the maximum amplitude and is denoted by TR, called a rise time. Fall time, the time taken for the collector current to reach from 90% of its maximum value to 10%. 90% of its maximum value to 10% is called initial value and is called fall time, TF. Storage time, time interval between the trailing edge of the input pulse to the 90% of the maximum value of the output is called the storage time. The time delay, TD, the time taken by the output current to reach from its initial value to 10% of its final value, called as time delay. This is actually the input pulse. This is the output pulse. When this pulse is moving from input to output, it undergoes such a change in shape and is measured in this way, that is a TD, TR, pulse width. Pulse width is generally measured between the 50% of the pulse rising as well as falling edge, not from a 0 to up to certain value. So it is exactly measured between 50% where it is averaged. So the width between this 50% of falling and rising edge is known as time pulse width, TD, TW. And so these are different characteristics of the pulse. Other, turn on time, the sum of the delay time TD and rise time TR is called a turn on time. The T on equal to TD plus TR. Turn off time is TS plus TF. Storage time and fall time, sum of storage time and fall time is known as turn off time. Gate is turning on, a logic circuit is turning on, turning off. These periods are depends upon TD plus TR, TS plus TF. Those depends upon the manufacturing of that gate or logic circuit. Pulse width, that time duration of the output pulse measured between 250% levels of rising and falling waveforms is defined as pulse width TW. SPP, speed power product. SPP is equal to TP, that is pulse period multiplied by power dissipation. Power dissipation, PD. Speed power product. Speed power product. TP is the pulse period. Pulse period multiplied by power dissipation, PD. It is called speed power product. Fan out, it is the ability of the logic circuit to drive number of load gates without loading effect. How many load gates? Without any effect, it can be connected or drive. It gives a status of output of the logic circuit. For TTL, its value is generally 20. Up to 20 loads it can be connected. For example, there is a charger. How many mobiles by extension pins we can connect for a single 5 volts charger that depends upon its power capability. So number of loads it can drive, or it can charge so many mobiles, say 20 mobiles, 10 mobiles, only 5 mobiles. That ability of the charger is known as its fan out. Fan in, it is the ability of the logic gate to accept number of input gates without loading. So this is input for the device. Suppose think that a mobile is charging through a number of battery chargers at a time, 5 volts, 5 volts, 5 volts. So because within short period we want to charge it, so that voltage remains same, but current will be in parallel. If you connect, current is more power supply will be there, easily, automatically, very fastly it will charge. This possibility is there in the logic circuits. So how many input terminals, for example, there is a OR gate, one pin A, another pin B, two input OR gate is there. So for A, how many inputs, again A1, A2, A3, A4, how many inputs it can able to tolerate, that ability is called fan in. The ability of the logic gate to accept a number of input gates without a loading effect is known as fan in. So this is the circuit. So number of input signals to the gate, that depends upon number of input pins. How many pins it has? One pin we can connect only one, not a 2, 3, 4 like that. So for one, how many inputs it has? Suppose 10 inputs, its fan in is 10. Only 2 inputs, its fan in is 2. So this is the NAND gate having fan in 8. Similarly, so fan out. Here, this is the NAND gate. So for this single NAND gate, we can connect 1, 2, 3. So many OR gates, negative OR gates are connected. So it can able to tolerate without loading effect. For generally TTL, it is 10. CMOS, it is up to 50. So this is the standard value. A logic circuit that specify to have 10 fan out can divide 10 logic inputs. The maximum number of standard logic inputs that an output can drive reliably. So this is the connection for fan out. So this logic gate can drive so many gates without any loading effect. Similarly, there is a logic levels for TTL gates as well as CMOS gates. For TTL, I already told 0, so 0 volts. So up to 0.8, it is low only. This is a logic low. When it crosses this 0.8, so it enters into what is called as unpredictable. So this is called forbidden. And above 2, again it starts entering into logic high. So 2 to 5 volts is logic high, 0 to 0.8 is logic low. So this 0.8 is called VL maximum. VL maximum. Whereas for high, VH minimum is 2 volts. VL maximum, VH minimum. So up to 2, exactly at 2 volts and above, it starts high. So in between, it is forbidden or invalid state. And these two are called logic margins of the TTL. 2 volts, 0.8 volt. VL maximum is 0.8 volts. VH minimum is 2 volts. For another type, this is 5 volts. Input output. For output, so this is for generally input circuit. So output logic 2.4 is considered as VO minimum and VOH minimum VIH it is. VIL, I for input, O for output. VOL maximum is 0.4 volts, 0 to 0.4 volts. This is unpredictable. And 2.4 volts is VOH minimum. VOH minimum. This is called VOH. This is called VOL. This is called VIH. This is called VIL. So in this way, logic levels for the TTL and CMOS has been distributed. So here high from 3.5 to above. Below 3.5, it is forbidden. So up to 1 volt. Few of the CMOS ICs up to 1 volts. VIH it is. This is this is VIL. This is VIH. VIH minimum. VIL maximum. This is up to 5 volts. The CMOS ICs which are working from 0 to 5 volts. Whereas CMOS ICs working from 0 to 4.2 volts. For these, the logic levels are 1 volt, 2 volt, 3 volt, like that it is distributed, but it is 4.2. High is only small range, 4.2 to 5. That is high. Above 4.2 it is high. Whereas for low, only 0.1 volt. Only 0.1 volt. This is input, this is output. So if it is a little bit more, exactly 0, 0, above 0.1, it is high. That is why, so care should be taken to differentiate CMOS ICs because they are very sensitive to voltages. This is input for CMOS. This is output level, logic levels for CMOS. And these are called logic margins. These are called logic margins. So here, this is high, this is low, disabled or forbidden state. And these are called logic margins. VO, VI. So these are for different values. The noise immunity. Another definition related to logic gates is noise immunity refers to the circuit ability to tolerate noise without changes in its output voltage. A quantitative measure is called noise margin. High state noise margin, low state noise margin, VNH, high state noise, NH, noise, OH, minimum, output high minimum, minus VIH, input high minimum. That will give you 2.4 volts minus 2 volts, which is equal to 0.4. With respect to voltage examples, it is given. Low state noise margin. This is high state margin, low state noise margin. VNL minus is equal to VIL maximum minus VOL maximum. This will give you VNL, noise margin. These are the different definitions related to TTL and CMOS IC characteristics. Logic families. Sir. Yes?
Sir, the physics class start ಆಯ್ತು sir ಈಗ.
Start ಆಗಿದೆ. Okay, okay. Time is over. So we stop here only. In the next class again we continue logic families. Okay? Thank you.